today's lecture we will continue our discussion about sample and hold amplifiers. Where we were discussing about successive approximation ADC and its usages, and then in that connection we were discussing about sample and hold amplifier. So, essentially if I had to digitize some analog input voltage, then we have analog input voltage that is given through a SH amplifier. SH amplifier it is given essentially then the output of the SH amplifier is given to A to D converter. That is the scheme, and then you get a digital output from the ADC. So, in this connection this we are here we are discussing about successive approximation ADC, we are discussing, and we had shown in the previous class how the successive approximation ADC is working and why you need a sample and hold amplifier, and we were discussing about sample and hold amplifier in the previous lecture. So, if you see in the previous lecture, the sample and hold amplifier essentially holds the voltage in the capacitor. So, if we see the detailed circuit of this, so you have a input voltage that essentially given through a amplifier. So, we want actually charge the capacitor. So, one possible circuit is that we can have very small capacitor connected here and then put at the output. So, we will have a, for example, a switch here. Then essentially what happens is VI and then the switch S1 and then the output, this is to ADC. So, this is the whole capacitor which charges up. So, essentially that VI here comes as a VI at this point when switch S1 is closed. When S1 is closed, the capacitor C, the capacitor charges up to VI. This needs some time to charge up, but the output impedance of the op amp is small, since R0 of the op amp is very low, the charging is very fast, essentially few milliohm resistance and then few less than 1000 pf capacitor, it charges up in a fraction of a microsecond. So, normally it is the settling time of the op amp that determines the time constant. Settling time of the op amp determines the charging time. After that normally it is less than 1 microsecond. So, here the charging is very rapid. So, then once it charges up, then switch off the S2, then switch off S2, switch off S1, switch off S1. Now, ADC start command can be given, can be given. During the conversion, the voltage and the capacitor should not come down, because if the capacitor is too small, then the input resistance of the op amp discharges this. So, during the conversion time capacitor should not lose too much charge. So, ADC takes normally few microseconds for conversion. So, during conversion the voltage in the capacitor should not decrease, and it should have a low should not decrease, and also it should have very low dielectric absorption. So, the sample and hold amplifier is essential for the conversion. Now, there are two types of sample and hold amplifier we can think of, or if we see the conventional circuits today, take for example PIC microcontroller. In case of PIC microcontroller, which is as inbuilt, it has a inbuilt 10-bit ADC, then it multiple channels, multiple in analog inputs, analog input channels. So, it also has inbuilt sample and hold amplifier. There is a inbuilt SHA. Let us see how one can use this one in a real life situation, and that will explain the issues involved in the A to D converter. For example, if I take PIC microcontroller, the most popular chip in PIC would be for example 16F676 microcontroller. It has for example many input channels, analog inputs are there, and then as a supply and then ground. So, Vin can be given in one of the channels, and then this is actually connected inside through the capacitor, and then there is a switch here, sample switch is there, and also there is a switch for channel selection. We have a switch for channel selection. So, essentially if I draw this one, if I have many input channels, we have one output, and then the switch actually connects either one of them. One of the channels can be taken from here, and this actually goes through a resistance and then a switch, and then to the input, the sample capacitor. For example, in the peak about 120 of capacitor is there, and this is about 1K resistance is there, and switch has some resistance. So, considering this, that equivalent circuit of the PIC microcontroller A to D looks like this. You have 1K resistance, and then the switch, and then there is another switch on when it is on, that has on resistance, and then it has another on resistance, and then about 120 of capacitor. So, this is about 1K that is there inbuilt, and then this is about few hundred ohms, and then this is also around few hundred ohms. So, about 1K resistance is there in series to charge up this. Then this ADC, the success of ADC is here, that is given as a ADC input. So, you have two switches, one is for channel select, that is given here, channel select resistance, and then this is actually to switch on and off the charging process. So, we can show it like this. In that case, we have a input voltage, then comes through a switch, then resistance, and then comes through a switch, and then to the capacitor, and then to the ADC. We make it ADC. So, you have channel selection switch and then charging switch, channel 1, channel 2, whichever which want can be selected, and about 120 EP of capacitor. Now, if I had to do the conversion, then first S1, S2, S1 and S2 are on first. Now, allow the capacitor to charge up to half LSB, because if it is a 10-bit converter. So, if it is a 10-bit converter, then we want 1 LSB accuracy minimum, then I should allow at least the voltage to charge here up to half LSB, so that I can allot half LSB error to this. So, if, that means if it is a VA is the input voltage, and then the capacitor charges exponentially, we have the input voltage, and then the capacitor charges exponentially to VA. So, you have the voltage actually and the capacitor comes as VA into e power t by RC. So, capacitor, then the question is how much time I have to wait, that is in the sample mode, how much time I have to wait, that is the question. So, how much time I have to wait, for charging, up to VI minus half LSB. Now, that actually we can solve this equation and see that VI actually comes as VI into e power t by RC. So, if I take this, if I simplify this, you get this equation. Now, V by VI actually V has to reach up to half LSB, that means if it is a 10-bit converter, that will be 2 power 10 bits are there, minus half LSB divided by 2 power 10, that is the time that you get this one. And if I take log both sides, then you will get it as ln of 2 power 10 comes 1024 because 256 into 4 24 to 22 to 1024 bits are there, minus half divided by 1024, that comes as e power t by RC. Now, if I take that one ln, that comes 1 minus 1 by 2048, that comes as t by okay, this goes off here, I take a log here. So, that actually t by RC. So, that comes t by RC. So, that comes ln 1 by 2048 equal to t by RC. So, the t actually can be determined depending on the time. So, this is the time t that I had to wait, so that it charges. Normally for this 1K and about 100 pf error, you will find out it comes 20 microsecond for R is equal to 1K and C is equal to 120 pf, this t comes about be 20 microsecond. So, in this case one had to wait minimum 20 microsecond for the capacitor reach half LSB. After reaching the half LSB, then I had to give a start command to the ADC. Then the third step would be after waiting for t seconds, start conversion should be given to ADC. conversion command is given to ADC. Now, ADC also at this stage the switch T2 is switched off. Once start conversion command is given, then the switch S2 is disconnected. So, now the capacitor is completely disconnected from the input, and then the conversion starts. At this stage S2 is switched off. So, you get the voltage, then you have the whatever voltage there in the capacitor actually goes to ADC. ADC takes its own time for the conversion. For example, if we take a PIC microcontroller, in PIC microcontroller, you see for 10-bit ADC, it needs 10 plus 1 cycle time for conversion. So, at the end of every cycle, 1 bit answer is available, 1 bit conversion answer, because first, as we discussed earlier, the conversion is done from MSB onwards. So, the conversion is done from the MSB onwards, is done from MSB most significant bit onwards. So, after say for example, if we leave the first conversion first cycle, then after the second cycle, at the end of second cycle you will have first MSB is ready, that is higher end bit is ready. So, at the end of second cycle, if we take a 8 bit a 10 bit converter. So, at the end of second cycle you answer this bit is ready, and the third cycle this is ready, and then the 11th cycle the converted bit, the LSB is ready. So, each cycle takes for example, minimum time is specified by the manufacturer. In this case, for example, minimum cycle time is 2 microsecond in this case. So, at the end of 20, that means for complete conversion, that is if I want complete 10 bit accuracy, then I have to wait for 11 cycles, that means 22 microsecond. For 10 bit complete conversion, wait for 11 into 2, that is 22 microsecond. So, at the end of 22nd microsecond, the conversion is over, and then invariably the interrupt flag is set. So, interrupt flag is set, and the conversion command will be known by that, or I can wait for this much amount of time, and then also I can read the contents from the register. So, the conversion takes a total of SHA time plus conversion time. In this case, this is about 20 microsecond, and this is about 22 microsecond. So, you will get about 42 microsecond is needed for the complete conversion, but in actual case you need more than this 42 microsecond. In actual case, we need to configure the channels, configuration of channels, that is channel selection, then input output selection and so on. There are various other instructions to be executed, which runs up to 10 instructions. So, all put together you may end up around 52 microsecond. So, all the other instructions can take all the setting instructions can take up to 10 microsecond. So, one conversion typically needs about 50 microsecond time, then only it is possible. It is the minimum time that is required for the complete 10 bit accuracy. So, the sample and hold amplifier is really a time consuming process, because if the sampling time is small, we can considerably reduce the conversion time. Now, there are various techniques that is used in ADC to reduce the time. So, let us see how to reduce the sampling time, how to reduce the sampling time. Similarly, you can also see how to reduce the conversion time of the ADC. Now, sampling time we can reduce by reducing the input resistance. So, one can, for example, if I want to digitize the voltage, now it is better to give through a voltage follower the input, so that the output impedance is very small. So, even if the source resistance is high, the capacitor can be charged very rapidly. Then only you will have a switch resistance that is come into play, and then this can go through the ADC can be connected here. So, if we take this, then it can go through a ADC. So, in this case the output, the only switch resistance is coming, which can be very small. So, the conversion time, the charging time can be reduced to few microsecond. In fact, there are two different types of sample and hold amplifiers commercially available. Now, one such a circuit is that you have a input amplifier, there you give a voltage follower this thing, and you have a switch voltage follower amplifier, and then you have a sample and hold capacitor that can be given, follower can be given to this. Then it can also be connected to the input, so that the total error is not there, and then upon charging one can disconnect the switch, then the output can be taken from here. This type of sample and hold amplifier gives the sampling time very low, 1 or 2 microsecond is possible to sample the voltage and keep it and the capacitor C, and the troop is determined mainly by the bias current of this amplifier. Now, there is another type of sample and amplifier, that is the second type. Second type, what can be done is that you can have a input can be given here, input voltage, then we can have a capacitor being charged, and this actually can be given to the plus amplifier. So, the output can come here. In this case it is good because that capacitor one end the charging end actually at the ground potential, and when you operate the switch for disconnecting the input, the charge injection is very low in this kind of amplifier. So, this is actually this type of SHA is popular. SHA will not induce, will not inject, will not introduce reduce additional charge, additional charge, additional charge, additional charge to the capacitor. And this also works extremely well, but in today's world the sample and hold amplifiers are rarely used because you know the additional overhead and then plus the time that it takes to charge and the other oscillations problem and so on, people are getting away with the sample amplifier and trying to find several other shortcuts to have a accurate conversion. Now, for example, one typical case we can take and then discuss about this in detail. For example, if you want to make for example, solar cell array street lighting using solar cells, if street lighting system to be designed, and if I had to use a microcontroller, that is a to D controller which is built in microcontroller, and use this for controlling the street light, solar street light. We see how this can be done, what are the options that is available to us. So, we take this example and discuss what are the possible thing that we can do to reduce the ADC time. So, solar cell based. Now, in this case what you do is we will take solar panel. For example, we have a solar panel which I show it as a series of diode equivalent circuit. So, which gives you a voltage here depending upon the intensity of the light that is falling on this, and then what is required is we have a battery, and then this battery is supposed to be charged. This battery is supposed to be charged whenever the panel voltage is higher than the battery voltage, and then we also have to do light switching actually, that is if I have a when the voltage is less, that is when the voltage is, for example, if it is a 12 volt panel, the voltage is lower than 3 volt, we can assume it is already dark and we can switch on the street light. Similarly, if the voltage is say more than 5 volt, then we can assume that it is sufficient light is there and the lamp should go off. So, it is essential that we have to sense the voltage of the panel and voltage of the battery, both are to be sensed using a ADC that is present in the microcontroller. So, in this case, for example, this is a 12 volt ADC, then I will take the for example, pick 16F676 I use, then I give this voltage, because the maximum or reference voltage that can be given is, say if it is 5 volt supply, it is only 5 volt. So, either I can use the reference for the A to D, it is the inbuilt power supply, that is this sorry, this 5 volt supply itself can be used as a reference voltage, or it is also there is a provision to use V reference external V reference. So, what is done is for example, if you are using 5 volt reference, which is a power supply reference, then this voltage should not be more than 5 volt, because at 5 volt then your output will be all 10 bits will be high, beyond that it cannot measure. So, I had divide this voltage and then given to the channel 1, for example, channel 1 it is given. Similarly, the battery voltage also to be divided and given to channel 2. So, this battery voltage, this is a panel voltage, solar panel voltage, and the battery voltage are fed to the PIC microcontroller for the conversion. Now, if we take this divider, we want very low current actually consumed from the solar panel. Similarly, battery also should not be discharged because this is all the time connected. So, we want to keep in fact very high resistance here, so that the discharge is very small, and also it needs a divider. For example, one possible solution is I can have 100K and then about 22K. So, 1 in 5 around you will get around 2.4 volt at the input. The same thing can be kept here, so that there is not much discharge. Now, in this circuit, if I see the converter inside, we have inside about 1K resistance, and then we have sample and hold capacitor is there inside. So, if I draw the equivalent circuit of this converter, it works out to be that I have a voltage source, and then the equivalent resistance would be 100K parallel 22K. So, the equivalent resistance would be 100K parallel 22K, and then it has 1K resistance, and then you have a switch resistance which I neglected. Then I have about 120 pf capacitor at the input. Obviously, this will take about 40 microsecond to reach half LSP of 10 bit converter, because the capacitor this is actually sample and hold SHA capacitor. So, we had charged the capacitor to half LSP, that is because it is a 10 bit converter. So, as we discussed, we have to wait for time t, that is equal to ln 1 by 2048 into RC, that is C, and the R is around 20, this will come around 20K, R is nearly 20K. So, if you see this, you may have to wait almost 40-50 microsecond to reach the half LSP level of close to half LSP of the V input voltage. If V input is 1 volt, then within half LSP of 1 volt to reach the within half LSP of 1 volt, we have to wait more than 40 microsecond. This is a quite a long time, because this is the main problem, because this resistance is higher, the input resistance is higher, because we are forced to keep very high resistance here, because we do not want to lose too much of power here. Similarly, the battery which is already connected, if a low resistance are used, they will be unnecessarily discharging, and by keeping this high resistance, we lost the enormous amount of time in sampling the voltage. Now, one easiest thing that can be done would be I can introduce an op amp between these two. So, for example, if it is a battery voltage, one simplest possible solution would be I can have a very large capacitor here, and then this can be given to this. So, very large capacitor, say 1 microfarad. Then it goes to the sample capacitor, which is 120 pf. Then it goes to ADC. So, say here in this case 100K and 22K. This is about 1K. Now, this capacitor does not lose much charge during charging. In that case, the voltage drop, if it is neglected, then we can ignore this situation, then the equivalent circuit actually becomes, you have a large capacitor and connected through 1K to 120 pf. This is 120 pf and this is 1K, and this is say Cx. So, as long as Cx is much larger than 120 pf, the input range is very low and the charging will be done quickly. but problem with this is if the battery voltage changes quickly, then this voltage will not change quickly, and then controlling would become very difficult. So, this method uh, charges the whole capacitor very fast, charges the whole capacitor very rapidly. But its system is not sensitive enough, fast enough to respond for the battery voltage change, but it is not fast enough to respond to the battery voltage change. So, and if you want very fast change, then you can use a voltage follower and then reduce the charging time. So, the battery voltage whatever we had, we can have this 100k and 10k, 100k and 22k. Then we can have a voltage follower, reduce the impedance, and this can be given to sample and hold. So, this is 100 pf. So, this actually goes to pick channel 1. So, channel 1 is given to this. So, the voltage follower gives a very low output impedance and preserves the voltage, and this works extremely well and reduces the charging time enormously low. So, practically is one of the possible way of reducing the whole time. Of course, the 1k resistance which is present still creates a problem, because there is no easy way to reduce that, because it is not, this resistance is not in our hand. So, minimum resistance comes in, and that minimum charging time to be followed, and that nothing can be done about it unless we make our own ADC. So, this is V battery voltage. For example, in this case, one can measure these voltages, for example, battery voltage and the battery voltage and the panel voltage, and then they can do the conversion very rapidly. In this case, conversion has to be very rapid. Unless conversion is very rapid, we will get into problem in this case, because for example, when we are charging the battery, we use this kind of circuit. For example, if you are charging the battery, see this is a panel voltage, solar voltage. Then if you are charging, normally what is done is that we will have our MOSFET is connected like this. Then we put normally the two and this side we connect to the battery, and then these two are connected to two gates are connected here. If I want to charge the battery, I will switch on, I will keep this one 0, and then we know that this has a diode, body diode is there, and then we have this. So, when this is connected to 0, for example, if gates are kept at 0, this is a battery, this is a solar panel. For example, if it is a 12 volt battery, if gates are grounded, then this is actually p channel MOSFET. It is a p channel MOSFET. So, when the gate is 0 and this voltage is high, then this gets on. Same thing happens actually. This is actually 12 volt and this is 0. This both MOSFETs will be on. That is both, I will say P1 and P2 both P1 and P2 are on. Similarly, if I give the gate 12 volt, if gates are kept at 12 volt, then P1 and P2 are off. So, we normally what we do is we will sense the through ADC this voltage, as we discussed, this voltage and this voltage are actually sensed. So, V P and V battery, V solar, Vs and Vb are sensed, and then once Vs is greater than, okay, this is V, I will put it as V battery is here, V battery, V solar, so if V solar is greater than Vb, switch on the keep the gates 0, put the gates put the gates to 0. Then the charging of the battery takes place. Then charging of the battery takes place. Now, as long as if the panel voltage is higher than the battery voltage, there is no problem and charging takes place. In case if because of sun going off, if the solar voltage comes down, then battery will discharge to the panel and the battery will get ruined and the panel also will get spoiled. However, if Vs comes down suddenly due to cloud or anything else, then it is required anything else, then battery will discharge to the panel. This will damage this must be stopped. This must be stopped immediately. That means one have to continuously monitor the battery voltage and the panel voltage, and within few microsecond, in case if the panel voltage is lower than the battery voltage, the switch to be the gates to be kept high. So, that is the P1 P2 must be switched off. So, if that means one have to sense very quickly, that is if V battery is greater than Vs, P1 and P2 must be switched off immediately. P1 and P2 must be switched off immediately. So, must be switched off quickly. So, it is essential that one does the conversion very one measures the voltage of the panel and the battery very rapidly and takes a decision and then switch it off at once. In fact, in a real life what they do is once the battery is once S1 once P1 and P2 are on, once P1 and P2 are on, the panel voltage actually started charging the battery. While charging, the resistance across this and resistance across this is resistance across this, for example, if we take the resistance across this is small few milliohms and this is also few milliohms, and if the charging current is 1 ampere, you will have a difference of only 40-50 millivolt between panel and the battery, because solar cell has a characteristics, as you draw more and more current, the voltage decreases. For example, if we take one single cell, the voltage characteristics will be like this. If I take voltage versus current, that you get curve like this. So as it draws more current, the voltage decreases. So essentially once you switch on the P1 and P2, voltage on the panel comes down. Of course, as long as the sunlight is there, the panel voltage will be higher, and suppose if the sunlight comes down, then the battery may discharge into the panel if it is not switched off quickly. And in addition, if these two voltages are since very close, battery voltage and panel voltage are very close, it is not easy to detect accurately and find out when the solar voltage are gone high or low, because for example, in the 10-bit converter, one LSP value would be can be calculated in the following manner. For example, in this case, V reference equal to 5 volt. It is a 10-bit converter. It is a 10-bit converter. So one LSP would be 5 volt divided by 2 power 10. That will be 5 volt divided by 1024. That will be 5 millivolt. That 5 millivolt at the input of the that is one LSP is equal to 5 millivolt at the input of the microcontroller. But then we have fed the voltage to the microcontroller through a divider arrangement, which is 100K and 22K. We have fed the voltage to the panel through this resistance divider arrangement. So the resolution at this point is 5 millivolt. So we have factor of 5 here. So this voltage is actually about 25 millivolt, that is 5 millivolt here you need roughly 25 millivolt. That means the ADC cannot detect more than less than 25 millivolt change in the in this case. That means if I take the minimum detectable voltage at the panel is 25 millivolt. Considering the voltage divider, the minimum detectable voltage at the panel is 5 millivolt into roughly that is 100K by 122K by 22K, that is actually roughly 30 millivolt. So below 30 millivolt it cannot be the minimum resolution of panel voltage measurement is about 30 millivolt. So minimum resolution at the panel is voltage resolution at the panel is 30 millivolt. Sometimes if the charging current is small, then you will not get 30 millivolt difference between the battery and the panel, because we have the two switches, the on resistance of the two switches which are actually very small. So, we have the on resistance of the is the battery and then the panel. So, the voltage difference between this point and then the battery, if it is less than 30 millivolt, the difference cannot be detected. So, to avoid this complication, what normally they do is that they will switch off the P1 and P2. So, in actual case they switch off the P1 and P2 for a fraction of a second, then measure the V panel and then V solar and then V battery, because when it is off, then obviously the voltage will be higher, it will be correctly known whether it is lower than battery voltage, because battery voltage is also known, you are measuring when it is off. So, if the battery if the solar cell voltage more than the battery voltage, only you will switch off. So, to detect accurately, the P1 and P2 are switched off, then Vp and Vp are measured, solar voltage and the battery voltage measured, and then the decision is made to switch on the battery. So, normally what is done is switch off P1 and P2, then measure quickly Vs and Vp. If Vs is greater than Vp, switch on P1 and P2. Keep this on state for about 3 to 5 millisecond. Then repeat from step 1. So, what is normally done is that you switch off, that is, if I show graphically, you switch off, then for some time, then switch on this, then go like this. So, here actually during this time, this is 0, P1 comma P2 are off. Here P1 comma P2 are on, that is charging, that in this case charging is taking place, charging of battery. So, this time is really the conversion time, there is because during this time when the P1 P2 off, no charging is taking place from the panel, it is a waste. So, during P1 and P2, during P1 comma P2, energy is not drawn from the energy is not drawn from the solar cell. That is, we are not utilizing the cell fully. Not utilizing the cell fully. So, P1 and P2 should be as short as possible. So, the off time should be very short, should be very short compared to the on time, compared to the on time. That is why the ADC must be very fast, that is ADC must be very fast. Of course, one may ask why not we keep longer on time. Why not longer on time? Longer on time can create a problem, because if the sunlight goes very rapidly, the if the voltage drops, then battery will be discharging for a longer time. So, we should not give longer on time. This is bad, because if V B is greater than V solar cell during on time, battery will be discharging. Battery will be discharging to the panel. So, to avoid that only it is done. We may ask that why not use a diode and then do one way charging only, but then diode will eat away 0.6 volt. That is why diode is not used. Diode is not used to block the reverse flow. Diode is not used to block the reverse flow. To avoid reverse flow, because diode will eat away 0.6 volt, eat away about 0.4 volt even if we use Schottky diode. So, to avoid this only this technique is done. So, in this case we need to have very fast conversion time, then only it is possible to utilize the solar panel the fullest extent. So, like this we can have many examples why we need a fast conversion, and then how one can achieve a fast conversion by reducing the sample and hold time, and then try to get higher fastest converter for our work. So, there are faster converter techniques, that is like for example, we have flash ADC converters are there, and that is much faster than success approximation ADC which we have discussed. So, we see about this flash ADC converter and so on in the next lecture. Thank you.